Covalent bonds are some of the most common bond types that we talk about in biology. These bonds are formed by sharing electrons between two atoms. So the key words here are really the sharing and electrons. So if you remember those two words, you should be able to really describe what a covalent bond is. Now the electrons that we're talking about that are going to be shared, these will be unpaired valence electrons. So these will be electrons that are in the very outermost shell of an atom, and specifically they will be unpaired electrons. And this means that it's very important that you do understand how to draw electron configurations, because you'll need to get that electron configuration to predict the bonding behavior of an atom. So if we look at an example of this, I'm going to start out with a very simple example. And so I have a hydrogen atom right here. And hydrogen has an atomic number of 1. So since hydrogen has an atomic number of 1, if it is a neutral atom, it's going to have just 1 electron in the valence shell. So ideally, it would have 2 electrons there next to each other. So it would be paired electrons only, or we would fill up that outer shell. So one way of doing that is for another hydrogen atom, and I'm going to draw it right here. Another hydrogen atom, which is also going to have 1 unpaired electron. Well, what these two can do is this hydrogen can share its electron with this one, and this one could share its electron up there. And then the end result of all of that is going to be that we end up with a covalent bond. So if I draw that end result right here, we have this hydrogen, and then we have this other hydrogen, and they each share their 1 electron with each other, and now we can call it a covalent bond. So as we see in the middle, this is the covalent bond. Notice that neither atom is really giving up its electron. It's just sharing with the other one, so that both of them now have paired up electrons. So 2 things that we want to happen when we form covalent bonds. First of all, we want to pair up all unpaired electrons. So notice that we have done that in this example. We had 2 electrons that were unpaired, or singles, or lonely electrons, if you will. And when we shared them with each other, now both of them had a partner. The second thing that we want to happen when we do this is we want to fill up the valence shell. Now, remember that different shells have different maximum numbers of electrons. So the actual number that we're shooting for in the valence shell is going to depend on the shell in question. In this case, it is the first shell, and recall that the first shell holds a maximum of 2 electrons. So as we formed this covalent bond, both of the hydrogens now have full outer shells, and this makes for a very stable, what we're now going to call molecule. So a molecule is when you have several atoms, and it could just be 2, but several atoms held together by covalent bonds. If we look at yet another example of a covalent bond, take some other atoms into consideration here. Suppose that we have a neutral atom of oxygen. Now oxygen, that's my nucleus there, oxygen has an atomic number of 8. So if we are dealing with a neutral oxygen, it's going to have a full first shell, so 2 would be on that shell. And then as we draw the second shell here, the second shell is going to have 1, 2, 3, 4, 5, and 6. So what we have is we have 2 places, right here and right here, where oxygen would really like to form covalent bonds. So remember that when we form covalent bonds, we want to pair up or share those unpaired electrons with another atom. Well, if we go back to our hydrogen example, remember that hydrogen, if we look at one hydrogen, it just has one electron on the valence shell. So one way that we could satisfy oxygen's needs here is we could take one hydrogen and put it right here, and then we could take another hydrogen and just attach it in the other position. So if I draw this one, so we could take that one and put it right there, and the end result of all of that, if we just draw it over here, is we have our oxygen nucleus there, and then I'm going to draw my oxygen shells. Remember, oxygen has 1, 2, put my other 6 oxygen electrons out here. And then if we draw in our hydrogens, we will have one hydrogen that goes here and one hydrogen that goes over here. And those hydrogens are both going to share one electron with the oxygen. Now, if we look at what the two things that we wanted to happen is we wanted all of the unpaired electrons to end up paired, which is the case here, and we want to fill up the valence shell. For the hydrogens, we now have 2 electrons in their valence shell, and that's the first shell. And for the oxygen, we now have 8 electrons in the valence shell. So we've satisfied the needs of all of the atoms that are involved. Now this molecule that we're looking here, common molecule, this is water, one that you're going to see quite a lot this semester. If we draw this molecule in a simpler way, we have our oxygen, and that oxygen is going to be connected to the 2 separate hydrogen atoms. Now remember that these lines that I've drawn here, those represent a covalent bond. And since they represent a covalent bond, each line is really 2 shared electrons. Okay, so 2 shared electrons. We can take these covalent bonds and we can classify them in a number of ways. And one of the ways that we can classify them is depending on exactly how many electrons are being shared, because it is possible to share more than 2. Every example that we've looked at so far, though, we've only shared 2 electrons. So these examples so far would be what we call single covalent bonds. And single covalent bonds is when you share 2 electrons between 2 atoms. And so in our water example, we're actually looking at 2 single covalent bonds. There is one single covalent bond between the oxygen and this hydrogen, and there is one single covalent bond right here. And we do designate a single covalent bond by just one of those dashed lines that you're seeing in this picture of the water molecule. Now, if we look at some of the other possibilities, so here I have 2 separate oxygen atoms, and again, oxygen, each oxygen atom has 2 unpaired electrons on its valence shell. So each of these, consider that if this one shared its electron there and this one shared here, and then we had the same thing happen for these other 2 that are unpaired. So in other words, if we had 2 oxygen atoms and each of those 2 oxygens share their 2 unpaired electrons with each other, then we get our next type of covalent bond. So this is where we get a double covalent bond. So with the double covalent bond, you're going to have 4 total electrons shared between 2 atoms. The simple way of drawing this, is it does get a little messier when we try to draw these with more than just one pair of shared electrons, is if we put our 2 oxygens there and we use those dashes to represent the covalent bonds. If it's a double covalent bond, you're going to see 2 of the lines in between those 2 atoms. And again, each line really represents 2 electrons. So we could draw in a little tight squeeze here, but if we drew in those dots to represent the electrons with each one of those lines, you can see that that is 4 electrons that we're sharing between those 2 oxygen atoms. Hopefully you can see the difference between what we called single covalent bonds with a single covalent bond between any 2 atoms. There are only 2 electrons. If we're talking double, we've got twice that. So we have 4 total electrons being shared. Now, it is possible to have triples as well. These are not going to be as common because there just has to be a little bit more unpaired electrons to make this work. But triple covalent bonds would have 6 total electrons that get shared between 2 atoms. So with covalent bonds, keywords again are sharing electrons. So we're sharing electrons, nobody's losing, nobody's gaining, but we share the electrons with each other so that number 1, all the unpaired electrons become paired electrons, and number 2, we do fill up the valence shell. And it's very important to be able to draw those electron configurations, because if we can draw those, then we should be able to predict how many covalent bonds any atom wants to make.